go. Hello. Good morning. Good morning, everyone. Morning. So nice. So the time currently is 7:12. I've been up since 6 a.m. The reason I was up at 6 a.m. because I was very excited. I was very excited because I have a new watch, I have a new fitness watch. It's Coro Space 3. My friend bought it from US and I've been wanting to like try it out on a run since yesterday. I got it yesterday and wanted to go yesterday morning. Last night I trained a bit, so I thought the ground was going to be muddy. Then I wanted to go in the evening to my friend's Lalit's place to run there, but it was also raining in the evening yesterday. So I slept. I didn't sleep early, but then I slept at like 12 o'clock and I did wake up this morning hoping to go run, but it was also raining in the morning. So that's also primary. Like I have been like busy with work yesterday evening, but that's why I couldn't like stream. I thought I woke up early. Why waste time? Maybe I should study something. I don't know. Nowadays, it's like if I'm trying to study something, I want to stream while studying it. So, still wearing yesterday's shirt. I went to office yesterday and I've been on the same shirt since then. I think it's fine. Okay, let's lock in. We already have some schedule. Let me pull that up. You see that? It says that. Anguish of choice. Such a fun screenshot. I should make a screenshot. Let me pull Notion up. We're also going to an offsite in 20 days. It's planned for like second week of October. Before I want to quickly check. So Perplexity has this like really nice feature where you can. There's this finance section which is like really nice. Spend like 15 minutes on this. This is the door. What is the Parquet? I think this is enough browsing. I like your door. Sister just opened. Random page that I have to clean up.
Need something better.
So you want to see this video?
So I'm from Netflix. Not sure how many people have heard of it. Video streaming on demand company. Oh, thank you. Great. Oh, my view is different. All right. I'm here to talk about Apache Iceberg. I work on Netflix's big data compute team. We work on all of the open source projects that make up our big data platform. So things like Spark, Parquet, Iceberg now, as well as the Hadoop, Presto, and projects that make up our big data platform. So things like Spark, Parquet, Iceberg now, as well as the Hadoop, Presto infrastructure that we use. Data compute team, we work on all of the open source projects that make up our big data platform. So things like Spark, Parquet, Iceberg now, as well as the Hadoop, Presto infrastructure that we use. So my team sort of spans all of those projects. And I've actually contributed myself to quite a few of them. I'm a Parquet committer, Avro committer, and Spark committer as well. Which means I've probably littered bugs into most of the code that you guys use, so sorry about that. So we're gonna start off by talking just a little bit about the goals that we had for the Iceberg project, or really what motivated us to create Iceberg in the first place. I think that I don't want to drop too big of a bombshell here at the end of the day, but what we found was most of our data engineers did not want to rewrite their SQL queries and reorder joins by hand. I know, I find it fun. They also didn't really want to tune their Parquet files. They didn't like going in and figuring out what block size to use or what dictionary page size is best for their data. They largely wanted to work on, strangely enough, getting new data sets in to satisfy their customers, and they wanted our platform to just work and continue getting better. And it was really kind of strange, but we decided to just run with it. And we set some goals for like the next 5 years, and this was a couple years ago, for where do we see our platform going? And really what we came to were a lot of pretty high-level initiatives for saving data engineers a lot of their time. Because again, on the one hand, they don't really care about join reordering unless it's slowing down their pipelines. And we're the ones on the data platform side that care about efficiency. They also don't really want to go sort their data and prepare it for the next level in the pipeline unless they absolutely have to. So we came up with, the direction of our data platform is that we should make all of those things more automatic, easier, and just speed up and make things better transparently, ideally without any interaction from our data engineers. But a problem at the time was that we were playing essentially whack-a-mole with this cobbled together architecture that is Hadoop and Presto and all of the other projects that make up the data warehouse. So we had unsafe operations just everywhere. If you're writing to Hive tables, chances are if you're writing to multiple partitions at once, that's not an atomic operation. In fact, you might, if you're overwriting a partition, you might delete a whole bunch of data and then hopefully replace it. There are just edge cases and sharp corners everywhere in these systems. Even something as simple as renaming a column is not a safe operation. It works in some systems, but if you rename like a CSV column, everyone's happy. If you rename a Parquet column, chances are you just broke a whole bunch of stuff. And then you have to detect it, come to us, and we say, oh yeah, you can't rename columns. And then you have to go fix it and backfill data, and it's an endless, really terrible process. We also are dealing with the fact that running natively on an object store like S3 causes a lot of major headaches. A lot of them we've solved, but when we solve one problem, it causes another. So we got atomic commits through our S3 committers, but then what we ended up with was not being able to actually append data. With the fact that running natively on an object store like S3 causes a lot of major headaches. A lot of them we've solved, but when we solve one problem, it causes another. So we got atomic commits through our S3 committers, but then what we ended up with was not being able to actually append data across partitions in our tables, which was a very surprising behavior for our users. Then we also have endless scale challenges. So what we decided to do was take a step back and look at both these long-term challenges as well as the whack-a-mole problem. Sorry, I went back a slide. You don't have to take pictures. We wanted to find what is the underlying problem that is causing all of these things. And what we found was it's essentially the table format. The main problems with working with an object store are that we do things like list files and directories and rename things in order to keep files out of those directory listings and on and on. And we found out that the table format itself was the bottleneck and what was causing all these problems and preventing us from building the data platform that we think we're going to need. So that brings us to Iceberg. Well, what is Iceberg? It's a scalable data format for tables that has basically a lot of best practices built in. And those best practices come from lots of smarter people that figured out long ago in database land that you don't track columns either by position or by name. You use a unique ID, right? So that you can have safe schema evolution with no side effects. If I rename a column, it actually gets renamed instead of changing the data in that column or only reading nulls. So what do I mean by format when I'm talking about a table format? That's kind of a weird thing, and most people think of a Parquet table or an Avro table or an orc table. Why am I talking about a format here? Well, what I'm talking about is really why am I talking about a format table or an Avro table or an orc table? Why am I talking about a format here? Well, what I'm talking about why am I talking about a format here? Well, what I'm talking about is really a table format. This is how do we manage a collection of files as this higher level abstraction we call a table. Now, most of the time we do it implicitly with Hive tables. So a good way of thinking about what a table format is and what we can do with a table format is to compare it to file formats. A file format really helps you track and modify or ignore a lot of data that's already in a file. So Parquet is a columnar file format. And because we organize the data in big chunks of columns, you can read individual columns from the file seeking without reading all the other data that you don't need, right? Table formats are similar. They're data that's already in a file. So Parquet or ignore a lot of data that's already in a file. So Parquet is a columnar file format. And because we organize with Hive tables. So a good way of thinking about what a table format is and what we can do with a table format is to compare it to file formats. A file format really helps you track and modify or ignore a lot of data that's already in a file. So Parquet is a columnar file format. And because we organize the data in big chunks of columns, you can read individual columns from the file seeking without reading all the other data that you don't need, right? Table formats are similar. How do we figure out which files we need from this table and ignore the rest of the files? Well, let's see how Hive tables do that. So the key idea behind a Hive table is to simply organize all of our data into a directory tree structure. I'm sure you guys have all seen this in your data warehouses or data lakes, I think is the current term. So Hive organizes all the data files in a directory tree. And that way, when I say, I want 2018, looks like May 13th, 7 p.m., I can go to that directory and list it, figure out what files are in that partition, and then just read those files, allowing me to ignore all the rest of the files in hour 18 or hour 20. And then this causes some problems. So what we end up with is we have to go list all the directories to figure out what days are there, and then we have to list directories to figure out what hours are there, and then we have to list directories to figure out what files are there. And we thought, that's too much directory listing. So what we're gonna do is we're gonna put half of this in a database. So we'll take all the directories themselves, stick that in a database we'll call the metastore, and then we'll just go and list all of the directories that are leaves in this tree structure. Now, this is pretty much the state of the art when it comes to the Hive table format. That's it. We can go figure out what directories exist, go list those directories, and then read all the data from all the files in those directories. Then we can use file formats, and it's great that we can use Parquet to skip row groups and things like that. But as a table format, this is basically state of the art. But I would argue that this is actually much more like CSV is to a file format as the Hive table format is to table formats. Because there's a lot that we're doing here that, this is just a very primitive, very difficult to work with structure, and it doesn't help us in a number of ways that it actually should. So first of all, if we look at problems with this, we're keeping state in two places. We're keeping state in a metastore, which keeps track of all our partitions. Then we're also keeping state in a file system. And we can't either, it's difficult to parallelize all these file system operations. We might have to list 1,000 directories to figure out all of the files that we need to read for a single query. And we also...
I'll take a quick pause. I want to understand these. What exactly is meant by a state? understand it a little.
Can't actually do more intelligent things. So then we're also keeping state in a file system. So first of all, sure, this is just a very primitive, very difficult to work with structure, and it doesn't help us in a number of ways that it actually should. So first of all, if we look at problems with this, we're keeping state in two places. We're keeping state in a metastore with problem like that's and read all the in 15 or hour 20. And then this causes some problems. So what we end up with is we have to go list all the directories to figure out what days are there, and then we have to list directories to figure out what hours are there, and then we have to list directories to figure out what files are there. And we thought, that's too much directory listing. So what we're gonna do is we're gonna put half of this in a database. So we'll take all the directories themselves, stick that in a database we'll call the metastore, and take what files are there. And we thought, so what we end up with is and then this causes some problems. So what we end up with is we have to go list all the directories to figure out what days are there, and then we have to list directories to figure out what hours are there, and then we have to list directories to figure out what files are there. And we thought, that's too much directory listing. So what we're gonna do is we're gonna put half of this in a database. So we'll take all the directories themselves, stick that in a database we'll call the metastore, and then we'll just go and list all of the directories that are leaves in this tree structure. Now, this is pretty much the state of the art when it comes to the Hive table format. That's it. We can go figure out what directories exist, go list those directories, and then read all the data from all the files in those directories. Then we can use file formats, and it's great that we can use Parquet to skip row groups and things like that, but as a table format, this is basically state of the art. But I would argue that this is actually much more like CSV is to a file format as the Hive table format is to table formats. Because there's a lot that we're doing here that, this is just a very primitive, very difficult to work with structure, and it doesn't help us in a number of ways that it actually should. So first of all, if we look at problems with this, we're keeping state in two places. We're keeping state in a metastore, which keeps track of all our partitions. Then we're also keeping state in a file system. And we can't either, it's difficult to parallelize all these file system operations. We might have to list 1,000 directories to figure out all of the files that we need to read for a single query. And we also can't actually do more intelligent things. So we can't get atomic commits if we have to make 1,000 files in our table live at the exact same moment. So this is the key insight behind why we thought we needed to make a new table format. This is just too primitive for us to even get atomicity when we're writing to these tables, so we need something better. That something better is what we hope will be Iceberg. But before we introduce Iceberg, I want to talk just a little bit about what Hive did really right. If you've seen my talks on Iceberg before, I didn't used to do this, but it's all about what Iceberg does right. But I think it's really beneficial to take a minute and realize what Hive did right. We're talking about Hive right now because Hive tables are simple, easy to understand, and ubiquitous. Because they were so simple, everyone said, oh, we can integrate that into our system. So what we have is support in all sorts of tools like Spark, Hive, Presto. You name the query engine, it probably supports this table format. And that's a really good thing, because what we've done is we've created this common layer of at-rest data that we all know how to work with. Then we also have additional tools for putting data into that format. So things like NiFi, Scoop, Hudi to a certain extent, Flume, all of these other tools, they work because everything has this lowest common denominator of the Hive table format. So it's a lot like CSV as a table format. It's primitive, it can be improved upon, but it's so ubiquitous that we don't want to lose that, that common layer, the at-rest layer where everything can work together. So let's talk a little bit about Iceberg. Iceberg is a table format where we've basically gone and said, if we were to design having a CSV and having Parquet, if we were to design a table format similar to the Parquet end of that scale, what would it look like? So first of all, it's going to look like an open spec, right? It's going to be something that we can all use for at-rest data interchange, so that we don't give up, I think, the biggest contribution of Hive, which is everyone uses the same format and we all agree on how things work. So we want a clear spec, we want it to be cross-language, we want it to be something that everyone can use. The panel about open source technologies and governance, this is a project at the Apache Software Foundation. It's Apache licensed. We really want this to be something that can be that ubiquitous at-rest layer. Next, we want to design to improve scale and reliability. We want it to be something where we can plan a job on a single node, but still store, say, tens of petabytes of data in a single table. We want those tables to be able to store tens of petabytes, but still be useful for jobs that don't want to read the entire thing, right? We need concurrent writers, et cetera, et cetera. And then we also want to fix the persistent usability problems that have come with Hive tables. Because Hive tables can use any format under the hood, we have things like the problem that you can't rename columns. Some formats you can't drop columns. What we want is to basically bring up the level of support to tables should work like SQL tables without any unpleasant surprises. Right? If you could do it in Teradata and you had a good idea of how it worked, you should probably be able to do it in our big data systems today. Unfortunately, that hasn't been the case, but that's what we're doing with Iceberg. In addition, some things that just fell out of the design were features like supporting time travel, supporting rollback, metadata tables for inspection, and things like that. So it's actually very user-friendly to work with Iceberg. You can go, say, select star from mytable.history and see all of the changes, including like what actually wrote all of those versions. So how do we do that? Again, this is just a very, very high level because we don't have a lot of time today, but the idea is basically we track all of the files in a table instead of tracking directories. And then we track additional metadata for each of those files. The additional metadata allows us to prune more aggressively all of those files by using like upper bounds and lower bounds for each column, much like Parquet provides an index over row groups and rows in that file. Iceberg provides a coarse index over the files themselves so that we can prune much more aggressively and really improve the table performance at a high level. So instead of speeding up individual operations and doing that hard stuff, we can just ignore a whole lot more data in most cases and come out better off. So we track snapshots that are a complete set of files in a table. It is the whole complete table state. And we get atomicity from using atomic transitions from one snapshot of state to the next. So readers come in, they read the latest snapshot, or maybe if they're time traveling, they can go backwards. Writers write a complete snapshot of the files in a table, and then we atomically transition from snapshot 2 to snapshot 3, the new version. In reality, it's quite a bit more complicated than that, because if we did that, it would be incredibly slow on writes, because you'd be rewriting the entire table state all the time. We don't have time to go into details, really, but just be aware that it works. We have essentially reuse across these versions, and we've got pretty good performance out of this so far, at least at Netflix. Really quickly, I want to point out one more thing that is pretty crucial for some of those things that I listed on the first slide about where we want the data platform to go, particularly like materialized views and some of those more advanced features, cost-based optimization. In this world, because we're tracking individual files, and we have very rigorous sets of files for each version of a table, we know exactly what has changed between version 1 and version 5. We also have accurate cost-based optimization metrics given the set of files that you're going to read for a particular scan. So it's very, very easy for us to provide better data so that we can meet that long-term vision, while at the same time having fixed all of those like paper cuts and whack-a-mole problems that kept popping up endlessly. Want to talk about, I was hoping 3 use cases at Netflix, but we don't have a ton of time, so we might just get to 1 or 2. The first one is we have running in production a table that is in the tens of petabytes range of data. This is log data coming from systems, and it's a very critical table. It's very difficult to work with, though, or was before we moved it over to Iceberg, because it was, tens of petabytes. Now we can actually do quite a bit more with that table because of the more aggressive pruning that the new table format gives us. We can run over months worth of time when we're scanning this table and doing analysis instead of days or maybe weeks. And that's been the case for most of the tables that we've converted. We can process faster, we can plan jobs faster, and we can also go over much longer periods of time. We also, the second use case that's really, really cool is we have that table that I was just talking about that's tens of petabytes. We load portions of it into an Elasticsearch cluster so that we can go and look up individual machines or devices and see what happened for debugging purposes. And that was a very, very expensive Elasticsearch cluster. I think it was something like in the millions of dollars. What we've done, and this was surprising, we didn't know that we were going to be able to do this, was we were able to replace an Elasticsearch cluster with an at-rest Iceberg table where we rewrite the metadata to group things by buckets, so that we have a scalable Presto cluster sitting on top of this Iceberg table, and we're able to shut off a multi-million-dollar Elasticsearch cluster. So that's pretty cool. We met the, I think, 2 to 5 second SLA of the reads for that cluster, which was pretty amazing. With that, I am out of time, and I would love to answer I am out of time for that cluster, which was pretty amazing. With that, I am out of time, and I was pretty amazing. With that, I am out.
ఇంకా పడుతుందా వర్షం?
Out of time, and I would love to answer any questions you guys have after this out in the lobby. Thank you so much for listening.
Hi, I'm Tim Berglund with Confluent. Today, I'd like to talk to you about Apache Iceberg. Iceberg is
Following the person I spoke to, but this Ryan Blue. He's from Netflix. Yes, from Netflix. He was just a senior at Netflix. Damn. This is the DM that I used to work with. Just wondered how they were connected. Okay. Want to summarize my notes and put it in a doc. I think is not that useful, so I'll just like mark it as done. This I just want to shift to work on sometime later. Let's do it today. Finish this bit. Let me just quickly go over my notes. Actually, I think the whole talk was super useful. But then I also feel like there was a lot of things that I didn't know about or have to like go back and study, so
So I'm from Netflix.
And this is good enough for today. That was quite a long video. Query engine, Hive is also query engine and table format. And let's go do it. Let me just take a pause here. I think we can end this stream here. I think it's good. Glad I did this. It's a nice session. It's 8 right now and it is not raining, so maybe I can still go for a run. We'll see. I don't know. My folks are going to take off my bike. Okay. I'll see you guys maybe in the evening, if not tomorrow or day after. Thanks guys. Bye.